Okay, that's me. Fine. We've done that part. Yes, I've worked on DirectX for a very long time, starting in 99, 95 with Direct3D, version 5. I think we'll see that in a bit. But this is what I would call a piece of silicon. Everything that we do in this business is really based on a technology that's enabled by the work that Intel does here, for example, which is they take a piece of sand and they carve it up until it's worth $500. So in this case, we've got what we'd say is a chip. And when I started in this business, we had a certain number of gates on that chip. And then every 2 years, for the last 20 years, someone has come along and shrunken that chip to where the area it takes is about half of what it was the previous generation. And then they did that again in 2 years. And what the question is, what do we do with that extra space? Well, we filled it back up with more transistors. Okay, and then in another 2 years, we did the same thing. We shrank that down. This fabrication technology basically revealed for us now another factor of 2 of transistors that we can now decide what to do with. And then we did it again, filled those back in with a new set of transistors. And we went through this, since I've started, about 10 generations now. So we've achieved basically 2 to the 10th increase in the total number of transistors that we've got to use for our digital technologies. And that little yellow square in the middle is basically the chip size in terms of transistors when I started DirectX 5 20 years ago. And so now the question, so everything we've done since then has really been taking this continuous stream of technology in the form of the transistors and then channeling it out to our users. Every person in this business is effectively trying to take that innovation that's coming out from these fabrication plants in the form of transistors and turn it into a package that people will actually pay money for. So whether you're a game designer or a graphics technologist or someone who's arranging these gates, we're all part of this same stream that's flowing these technologies out to users in the way that is ideally going to be as attractive as possible to them. And so this stream of innovation has basically built up an ecosystem around it of a large number of companies, all of which are participating in this. Like Google and Facebook, everyone is really tapping into this primary stream of new technology and funneling it out to users in ways that they think will be the most attractive to those users. So that's really the battle. How do we decide what to do each generation with the new batch of transistors that we have available to us as an ecosystem? And for example, do we spend a bunch of them more on processors and CPUs? Do we spend them on GPU cores that we can use for games? Do we put the USB controller stack in there now so that our joysticks and game controllers are more efficient? These are all the questions that all of us as an ecosystem are working with all the time. And so the thing I want to make clear is that this is not something where the people who make chips go and say, hey, we're going to do this because we feel like it. They actually look at what the customers want. The objective is to turn these technologies into something that people will actually pay money for. And so they found that people will pay a lot of money for games. And as a result, the silicon manufacturers have been allocating an increasing fraction of the total budget of transistors that are generated each process cycle to game and graphic-oriented technologies. And that is really because of the people in this room choosing to focus on those technologies and provide them in a way that's packaged to end users that causes them to increasingly buy more and more of these transistors in the form of games and the PCs that run them, and phones and other devices. So it's a two-way street. It's not just us accepting the stream of technology, it's us helping shape the direction in which it flows, helping decide where that technology is going to focus. So the way it works in the digital business that I work in, there's an entire stack as part of this ecosystem of people who are contributing to this decision making. The silicon process that we've already talked about, Intel's really great at fabbing silicon there, and they give us this new technology every year. But they have to work with us to decide exactly what shape those atoms on that die should take. On top of that, they provide a driver, which is basically a piece of software that helps their silicon become comprehensible to the higher level layers that are above, and also make it work consistently. Then typically there's an operating system on top of that the driver interfaces with, and in our case we have Direct3D, for example, as an API that runs on the operating system with its own runtime. And then there's this thing called a game engine, like Unity or Unreal. And then on top of that is why we're here today. All of these pieces and all of the different companies that contribute and deliver each of those parts of the stack are all participating in this process of how we flow this technology out into the customer, who at the top of the stack is actually the one who pays for all of this. So where does Direct3D fit in? It's that middle API layer. Its primary purpose is to create a common interface that allows, really fundamentally, any game can run on a variety of different chips, or conversely, any chip that ships can have a lot of different games that run on top of it. That's the value that we fundamentally add. And so every year when we have a new cycle come along, or a new generation of silicon come along, we have to make design decisions about what we think those transistors should be allocated to. And we can either spend them on new hardware features, which is obviously just directly changing the silicon and asking the silicon vendors like Intel, what can they do to make this chip work better in terms of moving those transistors around. We can also focus on improving the programmability of our products so that the new developers, for example, have an easier time to create the products that their customers eventually pay for. Or we can actually just focus on performance, optimizing the architecture of the stack that we've just described here to make it so that richer games can be created. And so this decision has been made, like I said, about 10 different times during the last 20 years of DirectX. And so when we first started, we had basically a sort of a sprite blit engine when in DirectX1 with Direct Draw. But then over that time, we've added these new features, we've added new versions of the API. And this last version, DirectX12, has really been one of the ones where we spent the most time focusing on improving the performance axis of innovation, where we've been enabling applications to get access to the hardware at a much lower level. Basically, DirectX12 is the most direct DirectX we've had. So we're working with all the vendors, we're working on all the devices, and we've got a really good focus on tools this time. The fundamental result of this, as far as impacting you guys, is that people creating a mobile game or playing a mobile game will be able to play it longer because the API is more efficient, more effective. We've also improved things that enable you to create more complex environments, even on the same piece of hardware. The efficiency overall of the API lets you create more sprites, more objects, more characters, or put more rich appearances on top of those. And then we've also made it so there are fewer glitches. The frame rate that you have when you're doing animation will be a lot more consistent. And then because we've optimized for the CPU performance, especially inside the driver, that leaves more CPU for you to put in things like game logic, and less of your chips are going to need to be spent on graphics performance. And then, yes, there have been some improvements on the way the GPU works as well, but those are probably less obvious to a casual game developer. Okay, so the challenge here is that the API, because it exposes more directly what's going on in the hardware, actually can be trickier to use. And so what we're seeing is that it's really something that's ideal for engine developers. Their companies are teams of people who are very, very good at using the hardware, and our API lets them do that very directly. It lets them take over more control of things that they used to be unable to access, that the driver used to have to do or the API used to have to do. And so if you're using an engine like this, all you'll see is really better performance. If you're working on an engine yourself, then when you use DX12, you've got a bunch more optimizations that you can now perform to take advantage of the low-level capabilities that your API now offers. Yeah, so this is just a list of some of the features. I talked about these at a previous event. There's a lot of information on the internet now. The dev lead for DirectX12, Max McMullen, has given a series of talks. Got a slide on the end that'll show them all. That outlines the results of each of these efforts that we applied. I'm just going to highlight a few of them in terms of what they actually mean for game developers, especially on the casual and mobile front, during the rest of this talk. So just a couple of the ones I selected here are these first 3 or 4. The first one, this concept of programmable shading, is something that was an idea that we had a long time ago, back in almost the X5 timeframe. Like, how can we give the programmer more control of the platform? And so that involved a very pervasive change to the stack. We had to talk to the hardware vendors, get them to change their silicon, add more processing capability, flexibility inside the ALUs. Had to work with the driver writers and say, basically, okay, guys, you used to think you were just poking a bunch of registers. Well, now you're going to potentially be compiling code. And I have to say, when we first did that, a lot of people were very scared. Having a piece of silicon that wasn't a CPU doing runtime compilation, it's actually worked out. That's the good thing to say. So I think these first 3 are the ones I'm going to talk about today, and we'll get right into that first one. So before we had programmable shading, Warren Spector saw this last time. That's Ultima Underworld. There's no GPU involved. The textures on the walls actually shimmered and crawled because they weren't perspective correct. But it was a full-on 3D immersive environment, one of the first that has ever been completed. But after the DirectX process, we iterated through that. Basically, annual product releases up through 2003 or so. We delivered the technology that I think this is the Source Engine, Might and Magic franchise title. And you can see basically the level of fidelity that was delivered by that process. Now, and really that was basically a consequence of us convincing the entire stack of participants in the ecosystem to support this concept of programmable shading. Now for DX12, this concept of multiple CPU parallelism is really one of the key innovations. The interesting thing is that Intel and the other processor companies recognized that they needed to go to multi-core 7-10 years ago. And so we all have quad-core machines. But it turns out that most games today really have a very tough time spreading work over more than 2 cores, typically. I mean, there'll be one for graphics, and then one for everything else, like networking and gameplay and AI and audio. And sometimes they can maybe spread those out over 2 or 3 cores. But the graphics always had to be on 1 core until DX12. And so now there's actually a reason to have more than 2 cores, really. You can really exploit the capabilities of a quad-core machine, potentially use even more. So you can see how this works. This green bar, the app logic, is all that stuff I talked about: audio, AI, gameplay. And it's relatively easily distributable across the processor cores. But under DX11, the graphics, which is that top bar, pretty much consumed 1 core, and then all the others had to wait. But with 12, we're able to distribute more of the graphics across all the cores as well, and the total frame time just drops massively. And the implication for you guys is, well, really it boils down to thermals. Your cell phone game can run cooler because it's using 4 cores at a much lower heat level than it would if it just ran 1 core. It's because of the way clock rates dynamically adjust. Okay, the other big change in DirectX 12 was reducing the CPU API overhead. That's really work that we were doing inside the OS and the runtime and inside the driver. And we basically just deleted it all. We moved rendering commands to be offline compiled on separate cores. We let you specify resource dimensions in a much more flexible way that doesn't involve as much validation by the GPU driver, and made it simpler and more explicit exactly where you need to synchronize access to a particular resource. And there is even some further level of parallelism that we'll talk about in a bit. So the result of that, this reduction in the API overhead, can be shown by this benchmark that 3D Mark, they added a new test to 3D Mark. The Future Mark guys updated it to basically validate number of draw calls per frame. And so what they do in this case is they have a procedural sort of city block generator that creates, cities obviously, and then they call that a huge number of times to make increasingly detailed cities. And the number of times they can call it is substantially better with DirectX 12. We saw numbers in that case for that scenario of about 10x. If you're mostly limited by the number of objects that you're trying to draw in a given frame, you can increase that number by about 10 times. And this is another example of the same sort of scenario. This is Ashes at the Singularity, where they're showing a battle with a large number of units. Well, this isn't really the whole number of units. As you zoom out, you'll note that the number of units visible in the world can grow substantially, and they're all still rendered. Every bullet, every laser blast, every smoke puff is another draw call. And so that means that we're able to portray scenes of a complexity that were just not feasible before DirectX 12. Additionally added this command called execute indirect, which lets you even more effectively batch up a larger number of draw calls and submit them all with effectively one transaction across the API. And that results in yet another factor of integer multiples in performance on top. So what this means for again, like I mentioned earlier, is that you can now have more sprites in your game, you can have more objects, more characters, more clutter, more decor, and then on each of the objects in it, you can have more textures, more materials, more bump maps, whatever, and still run at the same frame rate. Okay, now there's one more feature I wanted to highlight, which I think actually something John Petty brought up this morning, which is what we've done in DirectX 12 is we've basically busted open the GPU and exposed the fact that it's actually comprised of multiple separate processor elements inside. And each one of those can be independently now programmed in the same way that the GPU as a whole was programmed under DX11. This slide basically shows that you'd have a single GPU. You can create multiple threads of work to assign your CPU tasks to, but you only could have one effectively that was driving the GPU. With DX12, the GPU has been effectively exposed as being comprised of these different processors, and so now those of you who are really good at multi-threaded CPU programming can now do multi-threaded GPU programming as well. And so, for example, you'll see these copy engines. Those are cores that you can submit work to. You can create a command buffer, assign it there, assign work to it. It'll do copy operations completely independently of anything else that's happening on your machine. You can be hauling textures up into memory in the background or writing stuff out in the background without affecting the operation of the other cores on the die, other than potentially contention for memory. And then what we've also done is we've exposed these individual processors within the GPU as also effectively separate processors. We basically said, okay, this set here, those are your 3D rendering processors. And then we'll set another set of those and say, okay, these are my compute processors. And each one of those sort of groups of processors looks to the application like a single processor that has its own command queue. And effectively, that makes this GPU look like a dual core system. Then that's got a set of compute processors and a set of graphics processors, each one's that I can create my own command queue for. And so this chip now that used to have only one processor on it, basically a graphics processor, now has three. It's got N copy engines and a compute engine and a graphics engine, all independently controllable. And we provided kernel level mechanisms that let you synchronize the work between those and distribute it across them in a very efficient way. Now it's not easy. It's just as hard to do multi-core programming of your GPU as it was to do multi-core programming of the CPU. But again, a lot of these engine guys have been doing that for a while. They're starting to make it work really well, and they want the option to have that level of control over the innards of the GPU as well. Each one of these engines can have its own command queue. When we say queue, we just mean a port via which we guarantee sequential operations occur. There's no such thing as jumping to the front of the queue. It's not that kind of a queue. Yeah, and then we have semaphores and fences that can be used to control the scheduling of those relative to each other. So one example of using this is things like you would do a sort of an SLI or a multi-GPU scenario. We've done a prototype using an Intel system where we have one of the processors in the machine doing most of the 3D scene rendering. Then we have the copy engines take that 3D scene and send it over to the other GPU asynchronously. And that means that as soon as the copy engine starts that copy operation, that first GPU can start rendering the next frame immediately. It doesn't have to wait for the copy to be done. And then when the copy arrives at the second GPU, it can do the post effects. It can add the blurs and the glows and the particle animations or whatever else we need to do at that point. And get a net improvement in frame rate that way. In fact, the way we see the improvement in frame rate just depends on how fast the two GPUs are relative to each other. If they're both about the same speed, we can get like a 50% speed up. And we do have a prototype of this, but it should come out as a sample, hopefully, in the next month or two. Okay, so these are really the net benefits. And the thing I want to make clear is that even if you're not writing this code yourself, you're still going to get those benefits because here's the final slide. If you're an AA developer, you can use this code directly. You can write an engine. You can update your content to exploit these technologies directly. If you're sort of a mid-tier person and you don't want to get into things like multi-core programming either on the CPU or the GPU, we still have DirectX11. We added a bunch of functionality to that. It now has a lot of the hardcore capabilities that DX12 has in terms of fixed function logic. But the recommendation is for most people, especially in casual and mobile, is just go ahead and use an engine. Because we've been working for the past year and a half with most of these engine developers and getting them to optimize their engines for DirectX12. And so as long as you're using that engine, when that hardware that your system is on, when the chip is correct, when the engine has been updated, your game will just go faster. Now, one of the things I want to point out is if you want to start playing with this now, maybe you're working on a very simple game or a prototype or something where you don't need to have an entire engine, you can just start playing with the samples. We have the Visual Studio 2015 SDK up there. It now automatically installs the right SDK libraries as part of the IDE. It supports a bunch of fun tools that you can do, things like editing your GPU code directly in line, like that. We have templates for the DirectX and DX12 applications in the File New Projects menu. And then we're moving all our samples out onto GitHub. So there's a Microsoft branch of GitHub with all of our DirectX12 sample code there. The other thing I wanted to point out is if you go onto this website, channel9.msdn.com, and search for DirectX12, you will get an extremely detailed video description by the developer lead himself of all of the features in the product in DirectX12. Basically, as we developed the API, we shipped a few of the features last GDC, and then some last SIGGRAPH, and then some this GDC, and some right now. And as each one of those sets of features came out, Max would describe how they work. And so the total description of the API now is available by just watching those talks. Now, one of the other things I want to point out for casual developers is Visual Studio now supports Android and iOS. And we're working with them, we're working with the Visual Studio guys to eventually get to the point where you can create a single project that builds for Windows, Android, and iOS all off the same files, basically. So that should be helpful. And the other thing I want to point out is that if you target the Windows platform that development environment provides as well, you end up being able to span all of the devices that Microsoft supports, all the way down from our Windows Phone, tablets, two-in-ones, laptops, all-in-one, Xbox, HoloLens, and the Surface Hub. So there's the universal, it's called the Universal Windows Platform, and if you stick to those APIs that are universal, your same application can run on all these devices. So you may not want to put a game there, maybe you want to put your companion app there. That might be an interesting thing to do, because you could create maybe a more hardcore game for the Xbox, but have the companion game be available on all these devices. Anyway, that's really the summary of all this. We think the X12 is going to help you set up your game, scale up your performance and battery life, improve your richness of the world that you can express to your people, that your artists can express to customers, and then just deliver an all-around better experience over the next few years across all these platforms. And the other thing about all this, remember I talked about us shaping the ecosystem? Well, tell Intel what you want to see in their chips, tell us what you want to see in the API and in the chips, and we'll all work together to try to make that happen. So, thank you very much.